Hello all, welcome to the YouTube live session on conic sections. So in this class, we'll be continuing with the ellipse, which we had left the previous class. Those who are attending the session now, I would request you to type in your names in the chat box. Hello, good afternoon, Narita. So I'll start today's concept with the concept of pole and polar in case of an ellipse. Okay. So let me first load in a graph for an ellipse over here. Okay. Yeah. So what is a pole and a polar concept? So let P be any point inside or outside an ellipse. Okay. It can be even on the ellipse. Let's say there's a point P inside the ellipse, and through this point P you are drawing many chords. Okay, so let's say I draw this chord through this, and again I draw another chord like this. Okay, so I can keep on drawing so many chords, and now through the extremities of these chords, let me draw tangents. Okay, so let's say these are the two tangents which I draw at the extremities of these chords. Yeah, so these tangents, they will meet on a line which we call as the polar. So as you can see, they meet on this line, and this line is called the polar of this pole. So this point is called the pole. Okay. And also remember, this pole could be inside the ellipse as well. The pole could be pole could be outside the ellipse as well. Okay. Now the equation of the pole, equation of the polar with respect to a given pole x1, y1. So equation of the polar with respect to an ellipse for pole x1, y1. For pole x1, y1 is again given by t equal to 0. Okay, that means if x square by a square plus y square by b square equal to 1 is the ellipse, then the equation of the polar would be this. So this would become the equation of the polar. So as I told you earlier, t equal to 0 can behave as many things. It behaves as a tangent when the x1, y1 point is on the ellipse. It behaves as polar. So I'll write it down over here. It behaves as tangent when x1, y1 is on the ellipse. Okay. It's not that it is not polar in this case. It can also be called as a polar in this case. So tangent is the polar of the point of contact. So t equal to 0 can also behave as chord of contact. Now this is also a type of a polar when the pole is outside, and when t equal to 0 purely behaves as a polar, when the point is inside. When x1 y1 is inside. Right? So let us take some questions based on pole and polar. First question is, find the polar of the focus, or you can say find the polar of a focus of an ellipse. Very simple question. You should all be able to answer this. So I'm asking you, if pole is the focus, if pole is your focus, then what is the polar? And please feel free to type in your response in the chat box. How was your practical, guys, today? All right, so pretty simple. So again, let's say this is the equation of the ellipse, and we are trying to find out the polar of the focus. So focus is at, let's say, AE comma 0. So t equal to 0. So first of all, this is the expression for t. And here we'll be putting our x1 as AE and y as 0. So it becomes x equal to a by e. Right? And this is nothing but the directrix. This is nothing but the directrix of the ellipse. So just remember this as a theorem, that polar of the focus is nothing but the directrix. Polar of the focus in case of an ellipse is nothing but the directrix of the ellipse. All right. So let's move on to another question. Next question is, the perpendicular from the center of an ellipse x square by a square plus y square by b square equal to 1 on the polar of a point is constant. Prove that the locus of the point is x square by a to the power 4 plus y square by b to the power 4 equal to 1 by c square. Where c is the given constant over here. Where c is the given constant. So this constant over here is your c. If you're done, guys, you can also send me the snapshot on my WhatsApp ID. All right, this says, let's assume that the point is h comma k, right? So the equation of the polar will be t equal to 0, which is nothing but xh by a square plus yk by b square equal to 1. Now the distance of the origin, that's the center of the ellipse, from this polar is a constant c. So I can clearly write it as, first of all, I can just rephrase it as this equal to 0 and put 0 0 in place of x and y. So it will be mod of minus 1 by under root of h by a square whole square k by b square whole square equal to c. That means 1 by c is under root of s square by a to the power 4 k square by b to the power 4. So which becomes 1 by c square h square by a to the power 4 k square by b to the power 4. And you can always generalize this. You can always generalize this as x square by a to the power 4 plus y square by b to the power 4 equal to 1 by c square, and hence proved. Right? Again, be very, very careful with locus type questions because they're very, very important. Let me take one more. CD is a variable chord of the ellipse. Sorry. X square by a square plus y square by b square equal to 1. Always subtending 90 degrees at the center. Always subtending 90 degrees at the center. Show that the locus of the pole of CD, show that the locus of the pole of CD with respect to that ellipse is x square by a to the power 4 plus y square by b to the power 4 equal to 1 by a square plus 1 by b square. So basically the question says there is an ellipse, okay, and there is a variable chord that subtends a right angle at the center. Okay, that subtends a right angle at the center. All right. Now we have to find out the locus of the pole of CD. Okay. So let us say the pole of CD was, let's say, H comma K point. Okay. Now the equation of CD now will be XH by A square plus YK by B square equal to 1. Okay. Right. Now, if I have to find out the combined equation of OC and OD, that means if I have to find out the equation of the pair of lines OC and OD, right? How will I find that out? I can find it out by homogenizing. The equation of CD with the ellipse equation. So how do we homogenize? Remember the concept, when a line and a conic section gets intersected, the pair of straight lines joining origin to the point of intersection is obtained by homogenizing the equation of the line with the conic section. So when I say homogenizing, do not disturb the second degree terms of the conic, but this one term, this one over here, you can actually write it as XH by A square plus YK by B square whole square. Okay, because 1 is this, and you can write that 1 as 1 square. So from this equation, you can write x square by A square plus y square by B square equal to XH by A square plus YK by B square whole square. Now, you know it's 90 degree, that means it represents a pair of straight lines which subtends a 90 degree at the origin. That can only happen if the sum of the coefficients, let me call this as 1, sum of the coefficients of x square and y square in 1 add to 0. Okay, so what is the coefficient of x square? Coefficient of x square will be this. What is the coefficient of y square? The coefficient of y square will be this. And if this adds to 0, that would be the condition for the two lines represented by OC and OD to be at 90 degrees to each other. So if you write it in a resolved form, you'll find that it actually comes out as the required locus. So if you generalize this, it becomes x square by a to the power 4 plus y square by b to the power 4 equal to 1 by a square plus 1 by b square. And I think this is what we are supposed to prove. As you can see, yes, this is what we are supposed to prove over here. Right? Is this clear, guys? Any questions? Please feel free to ask. So the next concept that we are going to talk about is the concept of diameter. Now, first of all, how is the diameter defined? Diameter is basically focus of the midpoints of system of parallel chords. Focus of the midpoints of a system of parallel chords is called the diameter. Okay. So basically, let's say if this is your ellipse, Okay, and you draw a system of parallel chords like this. Okay, and start connecting their midpoints. Then this line that you see will be called, the white line that you see will be called as the diameter. So this line will be called as the diameter. Now let me ask this as a direct question to you. Find the equation of the diameter that bisects a system of parallel chords with a slope of m. So let's say we have our standard case of an ellipse, and all these chords, they have the slope of m each. Okay, then find the equation of the diameter. So that's the question. Again, feel free to type in your response in the chat box or send me a pic on the WhatsApp. Now guys, it's not important to know the concept of diameter per se, but how do you actually solve it as a locus question is what is important. Again, I'm repeating, the concept of locus is what I'm more interested in testing. Probably IIT will never ask you a question on diameter, but this is like a building block for you to understand locus very well. So the answer should be in terms of course, the variables x and y and a, b, and m only. We don't have to assume that that will actually be evident from the equation only. All right, so let's see this case. Again, let's say h comma k, whose locus we are finding. Okay. So h comma k is the midpoint of a chord. So what is the equation of that chord? If h comma k is the midpoint of a chord, what is the equation of that chord? Simple question. The equation of that chord is t equal to s1. Right? So T equal to S1. Correct? So this is the equation of the chord. Now this chord is having a slope of m. This chord is having a slope of m. Right? So let us write down the expression for the slope of this. Slope of this will be minus h by a square divided by k by b square. So this will be your slope. Right? And that's it. That's what we wanted. We wanted a relationship between h and k. Right? So now we generalize this. And we write m as minus b square x by a square y. In other words, y is equal to minus b square x by a square y, sorry, a square m. This becomes the equation of the diameter. And as you can see, Atmesh, it passes through origin. So yes, it passes through the center of the ellipse. It passes through the center of the ellipse. Okay, plain and simple. The next concept that we are going to talk about is the concept of conjugate diameters. So what is a conjugate diameter? So let me show you through a diagram. So let's say this is a system of parallel chords. Okay. And this is a diameter which bisects these parallel chords. Okay. So basically consider this to be bisected. Okay. And now if I start making all chords which are parallel to this diameter itself. Let's say I start making all the chords which are parallel to the diameter of this. Okay. Then the line, let's say this red line which bisects these chords parallel to this line. That is the red line. Okay. So what I'm doing first, all these white lines, this is the diameter. Okay. So let's say diameter 1. And these yellow lines, all these yellow lines, including the diameter itself, is bisected by this diameter, which is called diameter 2. Okay. So I'll write down the definition. Two diameters are said to be conjugate. Two diameters are said to be conjugate. When each bisects all chords parallel to the other. When each bisects all chords parallel to the other. So the red and the blue are conjugate diameters. Now please do not take this angle to be 90 degree. This angle is not 90 degree. I am writing it specifically over here. Okay. By the way, this will become a 90 degree had this ellipse been a circle. So let us take some properties. With respect to the conjugate diameters. Properties of conjugate diameters. The first property is the eccentric angle of the ends of a pair of conjugate diameters. The eccentric angle of the ends of a pair of conjugate diameters in an ellipse differ by a right angle, differ by 90 degree. Now guys, what I want to say is very, very clear. Focus on this diagram. So let's say this angle over here is let's say theta, and this angle over here is, let's say, phi. So these are the ends. Okay, let me name it as PQ. So this is P, this is Q, and this is C, and let's say this is D. Okay, so let's say the eccentric angle of point P is theta and the eccentric angle of point C is phi. Then you have to prove that these angles differ. These angles differ, right? You can write theta minus phi or phi minus theta. That depends upon what is the location of theta and phi with respect to each other. They differ by 90 degrees. Guys, it doesn't mean this angle is 90 degree. Again, I'm repeating this because the eccentric angles are taken with respect to the auxiliary circle. Am I clear? This doesn't mean the angle between the conjugate diameters is 90 degrees. Right? So can anybody prove this? All right, guys. So let's discuss this first. Before you prove anything else, I would like you to just try and prove this. Let's say the slope of diameter m1, diameter 1 is m1, and slope of diameter 2 is m2. Okay. Try proving that m1 m2 is b square by a square. That's the number one step. Prove that the product of the uh, product of the slopes of the conjugate diameters is minus b square by a square. And remember, since b square and a square are not equal, m1 m2 will not be minus 1. And if m1 m2 is not minus 1, the conjugate diameters cannot be perpendicular to each other. Yes, they would be perpendicular, but that would be a case when the ellipse has changed itself to a circle. Okay, so it's very simple, guys. How do we prove this? Let's say the blue diameter is bisecting the chords whose slope are m2. So I can write the equation of diameter 1 as y is equal to minus b square x by a square m2. Right? Because it is bisecting those chords which are having a slope of m2. Right? Any doubt about that? And the slope of this line itself, if you see, this is the slope of this line. Correct? And the slope of this line itself is m1. Which clearly means m1 into m2 could be easily proved as minus b square by a square. Right? So number one step is accomplished. Now let us move on to prove the requirement of this property. We have to prove that the difference of the eccentric angles at one end of the conjugate diameters differ by 90 degree. Right? Now this is origin. We all know that both the conjugate diameters will pass through the origin. Correct? Right? So what is the slope of OP? The slope of OP is nothing but b sine theta by a cos theta. In other words, it's b by a tan theta. Correct? And this is nothing but m2 for you. This is your m2. Right? In a similar way, what will be the slope of OC? Now, without waste of time, we'll say b by a tan phi, and that is going to be m1. And we already know this property that m1 into m2 is minus b square by a square. So I can say b square by a square tan theta tan phi is equal to minus b square by a square, which clearly implies that tan theta tan phi is equal to minus 1, which means 1 plus tan theta tan phi is equal to 0. Right? And if you try to use this formula tan theta minus phi, you know that in this expression you get the required expression to be this. And since this fellow is 0 over here, it makes this expression go 0. Correct? So it becomes undefined, which clearly implies that theta minus phi is going to be a multiple of 90 degree, and you can just call it as a 90 degree. Is that fine, guys? Any question with respect to this? Okay. And because of this property, if you say your point P, I'll draw the figure again just for the sake of clarity. So let's assume that these two are your conjugate diameters. Okay. So if this is your point P and this is your point Q, this is your point C and this is your point D, then point P could be written as A cos theta, comma B sin theta. Then point C could be written as minus A sin theta, comma B cos theta. Okay. And needless to tell you, how could D be written? Just increase theta with pi, so it becomes minus A cos theta minus B sin theta. And this could be written as A sin theta minus B cos theta. So for the sake of clarity, I have just written down the coordinates of the extremities of the conjugate diameters for you. Okay. Guys, next property, which is your property number 2. From this figure, prove that OC square plus OD square is going to be A square plus B square. Now this is very obvious from the property number 1. So just do it quickly and tell me if you're done. So just type done on the chat box when you're done. Guys, I don't think so it should take so much of time. It's very simple. OP is nothing but, oh sorry, this will be OP. Yeah, I'm sorry. So OP and OC square is just nothing but the distance of them. That means it's going to be A square sine square theta plus B square cos square theta minus 2AB sine theta cos theta, and OP square is A square cos square theta plus B square sine square theta plus 2AB sine theta cos theta. These two terms get cancelled off and you'd be left with A square. So these two terms will give you A square and these two terms will give you B square, and hence proved. Is that fine, guys? Any questions? Please feel free to ask me right now. Next property. The area of the parallelogram formed by tangents at the extremities of the pair of conjugate diameters, at the extremities of the pair of conjugate diameters is 4AB. So please prove this. So I've tried to draw it as accurate as possible. So let's say this is A cos phi comma B sin phi. And this point is minus A sin phi comma B cos phi. And this is the center of the ellipse. Again, P, O, C. So here you have to give the area of this parallelogram, M N, let's say S T. So you have to prove that area of the parallelogram M N S T is 4AB square units. Guys, if you see any parallelogram, okay, any parallelogram if you construct, we know that area of this parallelogram is base into height, right? So how can we use this concept over here to solve this problem? Guys, first of all, I would like to know from you that is CD parallel to the tangent at P? So my question to you is CD parallel to the tangent at P? If yes, please type yes. And is PQ parallel to the tangent at C? If yes, please type yes on the chat box. So guys, it's very simple to prove this. What is the slope of the tangent at P? The slope of the tangent at P, let me call it as slope of the tangent at P. Okay. So the slope of the tangent at P, no problem, Atmesh, that's fine. So slope of the tangent at P would be nothing but B cos phi by minus A sin phi. That's going to be minus A cot phi. And slope of OC is going to be B cos phi by minus A sin phi, that is y2 minus y1, right? Treat this as 0, 0, and you just have to do y2 minus y1 by x2 minus x1. And of course, they all match. So these two are same. It implies that the answer to these questions is yes. Yes, they are. Right? So if they are, it is something like this. I mean, you have a line like this, which is parallel to this line. And you have a line like this, which is actually parallel to this line. Right? Okay? And they're also passing through the point of intersection of the diagonals, that is your origin, which clearly implies that these four areas would be equal. Correct me if I'm wrong. This all area which I am shading, this area will be equal to this area, will be equal to this area, and will be equal to this area. So all these four areas will be equal to each other, right? So it's like saying that all these areas over here, okay, I'm shading with different slopes so that you can identify. Okay. So these all four areas will be equal. This will be equal, this will be equal, this will be equal. So if I just manage to find any one of them, my job will be done. So let us focus on finding out the area of this parallelogram. If I'm able to find the area of this green parallelogram over here, that is COPM parallelogram, and I just do four times that area, my job will be done. Right? So let us focus on finding the area of that parallelogram. So let's drop a perpendicular from the origin. Let's drop a perpendicular from the origin onto this parallelogram. Okay. Let me choose some other color, pink. Let me drop a pink perpendicular from the origin onto CM. So if I multiply OP or CM, so area of parallelogram COPM can be written as, let's say I drop a perpendicular called, let's say, OL. So OL into CM, which is actually as good as OL into OP. Now OP is easy to find out. OP is under root of a square cos square phi plus b square sin square phi. So no problem in finding OP. Now OL is nothing but the perpendicular distance of origin from the tangent drawn at C. Guys, just remember one thing. The equation of a tangent drawn at any point on the ellipse is going to be x(x1) by a square plus y(y1) by b square equal to 1. And here I am drawing it at x1, which is equal to, so your x1, y1 point are actually minus a sin phi, comma b cos phi. So if I use this equation, the tangent equation would be, tangent at C would be x by a square into minus a sin phi plus y by b square into b cos phi is equal to 1. So cross the factor of a, it will become minus x sin phi by a plus y by b sin phi minus 1 equal to 0. So now I want the distance of this point from the origin. So the distance of this point from the origin, so the distance from origin, or distance of origin, I can say, distance of origin from tangent at C is equal to 1 by under root of sine square phi by a square plus, this is going to be cos, I'm sorry, just a typo error. So cos square phi by b square, which is actually ab by a square cos square phi plus b square sine square phi under root, right? So when you put these two things over here, that is, this is nothing but your OL. Okay. So when you substitute it over here, this and this, you get your area as AB by under root A square cos square phi plus B square sine square phi into under root of A square cos square phi plus B square sine square phi, which gets cancelled off, and we get the area as AB. Now, as I already discussed with you, the area of the required parallelogram would be 4 times the area of the parallelogram COPM. So your answer would be 4 times the area of parallelogram COPM. So your answer is going to be 4 times AB. Okay, and hence proved. Whew. Is that fine, guys? Let us try to do some questions which are based on the conjugate diameters. Show that the tangents at the ends of conjugate diameters of the ellipse x square by a square plus y square by b square equal to 1 intersect on another ellipse whose equation is x square by a square plus y square by b square equal to 2. So very simple, guys. You should be able to do it within 2 minutes, I guess. Is that done? So guys, this concept is quite easy. Let's say you want to draw the tangent at, okay, let's go back to the previous page, or let me draw it here itself. Let's say these are the two conjugate diameters, right? And you are planning to make tangents at the ends of these diameters. Okay, so I have to find the locus of this point h comma k, right? So guys, pretty simple. Let's say this point is a cos phi comma b sin phi. Then this point here would be minus a sin phi plus, comma b cos phi. Okay, let's write on the equation of the tangent at this point. So this tangent equation would be x by a cos phi plus y by b sin phi equal to 1, right? And for the other point, you just don't have to do anything else. You just have to replace your x1 with minus a sin phi. So it will become minus sin phi plus y by b cos phi equal to 1. So guys, from these two equations, my aim is to eliminate phi, right? So if I want to eliminate phi, the process is pretty simple. Let me call this as 1. Let me call this as 2. So I will do 1 square plus 2 square. So when I do that, I'll get x square by a square cos square phi plus y square by b square sin square phi plus 2xy by ab sin phi cos phi plus x square by a square sin square phi plus y square by b square cos square phi minus 2xy ab sin phi cos phi is equal to 1 square plus 1 square, that's 2. And if you see, these two terms will get cancelled off. These two terms will get cancelled off. And you can club these two terms together. You can club these two terms together, and you can also club these two terms together, thereby giving you the required locus of their point of intersection, right? That's going to be 2. So this is another ellipse. So the locus of the point of intersection of tangents drawn at the extremities of, or at two ends of a pair of conjugate diameters is going to be an ellipse. So guys, next concept that we are going to discuss now is the concept of director's circle. Okay. So how do you define a director's circle? So it's the locus of the point of intersection. Locus of the point of intersection of two perpendicular tangents drawn to the ellipse. Okay. So again, assuming this is your ellipse, so the locus of a point h comma k, from where if you draw two tangents to the ellipse, these two tangents will be at right angles. So this locus would be a circle which is called the director circle, and prove that the director circle for the standard ellipse, the equation of the director circle is x square plus y square is equal to a square plus b square. So I would like all of you to please prove this quickly and type done if you're done with that. Yes, anybody has any idea? All right, so we'll try to use the fact that the equation of the tangent in the slope form. We all know that the equation of a tangent in the slope form is y equal to mx plus minus under root of a square m square plus b square, right? And since this point satisfies this line, I can say k is equal to mh plus minus under root of a square m square plus b square. That means k minus mh whole square is a square m square plus b square. That is k square plus m square h square minus 2mhk is equal to a square m square plus b square. That means m square h square minus a square minus 2hkm plus k square minus b square equal to 0. Now this quadratic equation has two roots, m1 and m2 are the roots of this quadratic equation. Okay, and if m1 and m2 are the roots, we all know that since the slopes are, since the lines are perpendicular, the product of the slope m1 m2 should be minus 1. So we know product of the roots is equal to c by a. So k square by b square by h square minus a square, that is equal to minus 1, which is nothing but k square minus b square is a square minus h square, which means h square plus k square is equal to a square plus b square. And if you generalize it over here, we get x square plus y square as a square plus b square as the equation of the director circle. Is that fine, guys? Any question with respect to this? So let us take a question on the director circle. Tangents at right angles are drawn to the ellipse x square by a square plus y square by b square equal to 1. Show that the locus of the midpoints of the chord of contact the midpoint of the chord of contact is the curve x square by a square plus y square by b square whole square equal to x square plus y square divided by a square plus b square. Yeah, guys, any idea? If done, please type done. All right, so let's take the situation through a diagram. So let's say this is a chord and its midpoint is h comma k. This is a chord of contact made by tangents from point x1 y1, and these tangents are at 90 degree. Okay. So first of all, can I write down the equation of a chord whose midpoint is known to me? Of course, we can write down the equation of a chord whose midpoint is known to me as t equal to s1, right? So if you write that, you are going to get xh by a square plus yk by b square is equal to h square by a square plus k square by b square. And in a similar way, I can also write down the equation of a chord of contact drawn from x1 y1. That is nothing but t equal to 0. So x1 by a square plus y1 by b square equal to 1. Right? Now, ideally speaking, in these two equations stand for the same thing, AB. So these two are actually the equations of, these both are actually the equations of AB. And hence they are same. So if they are same, I can compare the coefficients of x, y and the constants on both the sides. So if they are same, comparing the coefficients of x, y and constant, we get something x1 by h, y1 by k is equal to 1 by h square by a square plus k square by b square, right? Which means x1 is h by h square by a square plus k square by b square. Y1 is k by h square by a square plus k square by b square. Now guys, clearly speaking, this point x1, y1 over here, this lies on the director circle. This lies on the director circle. You cannot deny that because it's already given that this angle here is a 90 degree. So this has to lie on a director circle. And if it lies on the director circle, then you would not deny that the director circle equation should be satisfied by these 2 points. Oh, sorry, satisfied by these 2 coordinates. So these two should satisfy x square plus y square is equal to a square plus b square, right? Which means h square plus k square by h square by a square plus k square by b square whole square should be equal to a square plus b square, right? So if you just simplify this a bit, we'll get h square by a square plus k square by b square whole square will be equal to h square plus k square by a square plus b square. Okay, and now we can generalize this. And when you generalize this, you get x square by a square plus y square by b square whole square is equal to x square plus y square by a square plus b square, which is the required locus and hence proved. So guys, any question, please feel free to ask me. So if this is fine, let's take a break now. And on the other side of the break, I will start with hyperbola. So we'll take a break. Okay. And this break will resume at 5:40 p.m. And I'll start with hyperbola. All right, so welcome back from the break. So I'm going to begin with the basics of hyperbola in case you have forgotten it. Just a quick recap we'll do. Okay, so just the basic concepts. We'll recap of a hyperbola. Again, hyperbola is basically defined as the locus of a point which moves in a plane in such a way that its distance from a fixed point, which is the focus. Okay, so I'll just quickly write it down. So it's the locus of a point which moves in a plane, such that its distance from a fixed point, which we normally call as the focus, is e times its distance from a fixed line. That's called the directrix. And this e value is greater than 1. Right? So just to quickly sketch a hyperbola. In fact, I'll try sketching it on the GeoGebra tool so that you have an exact idea of the shape of a hyperbola. So I'll just sketch x square by let's say 36 minus y square by 25 equal to 1. Okay, so probably I've taken a bigger value. Let's say I take 9 over here. 9 and this is 4. All right, so this is basically the diagram of a hyperbola. Okay, so focus of this conic C, as you can see, it is at point A and B. And directrix of this conic C, as you can see, is this line F and G on your screen, right? So what I'll do now, I'll just take a snapshot of this so that I don't have to sit and draw this every time. Right there. Yeah. So let's go back. So I don't know this line anymore. So I'll just dump it. Yeah. Yeah. So this is your hyperbola. Now, the equation of this hyperbola, I will not derive it. We have already learned in our class 11. So x square by y square, x square by a square minus y square by b square equal to 1 is a standard form of a hyperbola, where the foci, where these foci, okay, so let me name the foci as a and b. They are called the foci. The foci are taken as ae comma 0 and minus ae comma 0. Okay, so these are the foci of the ellipse. Sorry, hyperbola. Okay. I'll actually write them down so that you can just read it from the graph. This is ae comma 0 minus ae comma 0. Okay. And these two are called the vertices. Okay, the vertices is at a comma 0, and this is at minus a comma 0, and this is x equal to a by e, and this is x equal to minus a by e line. All right. Now, quick things about the hyperbola. So, normally what you saw here was a hyperbola like this. Oh, sorry, hyperbola like this. You could also have a hyperbola where the equation actually becomes this with a minus 1 over here, and this is called the conjugate of this hyperbola. Okay, so this is called the conjugate of the previous hyperbola. Okay, so just a comparison chart between them. So this pink border. Graphically speaking, these two graphs would be like this, and this would be like this. So the orientation is different. Here your x-axis is basically containing the transverse axis. Okay, so this is your transverse axis, and this is called your conjugate axis. And here this is your conjugate axis, and your y-axis becomes the transverse axis. Y-axis becomes the transverse axis. Okay, in both these situations, this will be the center. Okay, so I'll just keep writing them now. So center for both of them would be 0 comma 0. That is something which you all know. Foci, before foci we'll talk about vertices. Vertices would be a comma 0 minus a comma 0. Here it would be 0 comma b and 0 comma minus b. Eccentricity, 1 plus b square by a square under root, and in this case it will be 1 plus a square by b square under root. In both of these cases, it's actually the length of eccentricity is given by under root of 1 plus the semi-conjugate by semi-transverse square. So this is a universal formula for eccentricity. So please keep this in mind. All right. Yeah. So foci. Foci is at AE comma 0 and minus AE comma 0. In this case, it is 0 comma B and 0 comma minus B. The equation of the directress is x equal to a by e and x equal to minus a by e. Here it is y is equal to b by e and y is equal to minus b by e. Length of transverse axis. Length of transverse axis is 2a units. Here it is 2b units. And length of conjugate axis, here it is 2b units and here it is 2a units. Okay. Length of the lattice rectum. Length of the lattice rectum, again 2b square by a units. And in this case, it will be 2a square by b units. So just a quick recap. I mean, I knew you already knew this, but just in case it has slipped out of your mind. Okay. Now, we'll talk a bit about the formation of an equation of a hyperbola given its directrix and focus and eccentricity. So we'll start with questions on the basic definition of a hyperbola. So let us begin with this question. Find the equation of the hyperbola. Find the equation of the hyperbola whose directrix is 2x plus y equal to 1, whose focus is 1 comma 2, and whose eccentricity is root 3. Whose eccentricity is root 3. If you're done, please type in your response in the chat box, or you can message me on my WhatsApp. Again, we'll use the basic definition. The distance from the focus should be e times the distance from the directrix. So let's say the point is x comma y. Directly we can assume x comma y instead of wasting time taking h and k. So the distance from 1 comma 2 is e times the distance from the directrix. Okay. So let's take the root 5 on the other side and square both the sides. So we'll get 5 times x minus 1 square y minus 2 square plus 3 times 2x plus y minus 1 the whole square. And if you open the brackets, you will be getting 5 x square plus y square minus 2x minus 4y plus 5 is equal to 3 times 4x square plus y square plus 1 plus 4xy minus 2y minus 4x. Okay. And simplifying it will give you 7x square minus 2y square plus 12xy. And then we'll have plus 14y. And we'll have a minus of 12 and 10, which is minus 2x. And 25 minus 3 is minus 22 is equal to 0. So this is the desired equation of the hyperbola. Is that fine, guys? Now we'll quickly take up some question on the general form of a hyperbola. When I say general form of a hyperbola means its origin is no longer at, sorry, its center is no longer at origin, so it is of this nature. So these cases are called this or this. So these cases are called the general form, where the center of the hyperbola is not at the origin. Okay. So what I'll do is I'll start off with a question. Okay. Directly asking you some of the critical points. Okay. So in this case, the center is at plus minus alpha comma plus minus beta. Okay. However, the transverse axis and the conjugate axis are still parallel to the x and the y axes respectively. So let's take a question on this. Find number 1, center. Number 2, vertices. Number 3, eccentricity. Number 4, let's say foci. Number 5, let's say equation of the directrices. So find these parameters for 7y square minus 9x square plus 54x minus 28y minus 116 equal to 0. So guys, please start solving it, and this time I want you to give your responses because I can see no response coming from any one of you. All of you are like mute spectators. Nidhish, are you there? Please type yes if you're there. So Yuja, type yes if you're there. Snigdha, type yes if you're there. Lalita, type yes if you're there. Anybody who's live, please type in your name right now. So Rohan is online. Okay, great, Rohan. All right, guys. So finding the center, there are a lot of methods. One of the method is the partial derivative method. So let's say I call this term as S. Okay, you can find out the center of any conic section by solving these two equations simultaneously. Solving these two equations simultaneously. Dou s by dou x equal to 0 and dou s by dou y equal to 0. If you solve these two simultaneously, you will get the coordinates of the center. Okay, so I'll try this method as of now. So partial derivative of this with respect to x, if you do, we get minus 18x plus 54 equal to 0. That means x is equal to 3. If you do a partial derivative with y, you get 14y minus 28 equal to 0, which means y is equal to 2. So you can say 3 comma 2 is the center of this particular conic, right? So the use of this partial derivative can be to find out the center only, not for any other thing. So if I try to solve it by our regular method, the method that we have learned in our class 11th, right? So we need to complete the squares. So first we need to group up terms having y's. So let's say I group up these two terms. Then I group up terms having x. Okay. And now we are trying to complete the square over here. So it becomes 7y square minus 4y. X square minus 6x minus 116 equal to 0. So let's complete the perfect square. This will be y minus 2 the whole square. This will be 9x minus 3 the whole square. And you have to compensate by adding 28 and minus 81 on the other side. So you get 7y minus 2 the whole square minus 9x minus 3 the whole square is equal to 63. That gives you y minus this by 9 minus x minus 3 square by 7 equal to 1. In other words, you can write down the equation of this hyperbola as x minus 3 square by 7 minus y minus 2 square by 9 equal to minus of 1. Now, if you want to get the center, please note that the center of the hyperbola, let's try to do a role change over here. Let's try to do a role change over here. Let's compare this equation with, let's compare this with x square by a square minus y square by b square equal to minus 1. So it's obvious that x is now, the role of capital X is now being played by small x minus 3. Role of capital Y is now being played by small y minus 2. Your a square is 7 and your b square is 9. That means a is root 7 and b is 3. Okay. Now we are trying to find the center. For center, we know x is 0, y is 0. That means x minus 3 is 0, y minus 2 is 0, which means x is 3, y is 2. So 3 comma 2 is your center. Okay. The next question was, vertices. The next question was the vertices. So vertices in this case is 0, comma b and 0, comma minus b. But instead of writing it like 0, comma b and 0, comma minus b, I would suggest write it like x is 0, y is b. That means x minus 3 is 0, y minus 2 is b. B is going to be 3. Right? So 3, comma 5 is one of the vertices. The other vertex is at x equal to 0 and y equal to minus b. That means again x will be 3 and y minus 2 is minus 3, which means y is minus 1. So 3, comma minus 1 is the other vertex. Right? Next is the focus. Sorry, the eccentricity. Eccentricity in this case will be under root of 1 plus a square by b square. So which is 1 plus 7 by 9. That's going to be 4 by 3. So eccentricity is going to be 4 by 3. Right? Next is focus. We know that for focus or foci, in this case, x is equal to 0 and y is equal to plus minus be. So I'll take these two cases, x equal to 0, y equal to b. So x minus 3 is 0 and y minus, let me write plus minus directly, y minus 2 is equal to plus minus be. So that gives you 3 as x, and y could be 2 plus minus 4. So y could be either 6 or y could be minus 2. So 3 comma 6 and 3 comma minus 2. Oh, sorry, 3 comma 6 and yeah, that's fine. 3 comma 6 and 3 comma minus 2. Okay. Now directrices. So the equation of the directrices would be y is equal to plus minus b by e. Okay. So y in this case is y minus 2 is equal to plus minus b by e. So that will be this. So y is equal to 2 plus minus 9 by 4. So your y could be 17 by 4 or your y could be minus of 1 by 4. Okay. So this basically helps you to understand the initial concepts that you had learned in your class 11th. Next question. Find the equation of the hyperbola whose foci are at minus 4 comma 4 and 6 comma 4, 6 comma 4, and eccentricity is 2. Yes, Nidhish. Nidhish, you're there? Nidhish, what's your response on this? Sayuja? Sayuja? Snigdha? So first draw the diagram for this. Everything will be very evident from there itself. So your foci is at 6 comma 4 and minus 4 comma 4, right? So let's say one is 6 comma 4 and the other is at minus 4 comma 4. Okay, so yes, this is the nature of your hyperbola. Okay, remember the center of this hyperbola will always be at the midpoints of, always be on the midpoint of the line connecting the two foci. So this will be your center, and center will be the midpoint, which is going to be 1 comma 4. Center is going to be 1 comma 4. Okay, so all of a sudden I have seen the attendance, the number of people watching has grown up. So it's important to call people's name few times. Right, now how will I get my A and B? Okay, very simple. The distance between the two foci is 2AE. So it is basically 10 in this case, right? So the distance between, let's say, S1 and S2 is 2AE. Okay. So E is given to us as 2. So A becomes 5 upon 2. Right? Now it's a case where the eccentricity is 1 plus B square by A square under root. So E square is 4. B square is unknown. And A square is 4 by 25. So this implies B square is going to be 75 upon 4. Now we can always write down the equation of the hyperbola once we know A square, B square and the center of the hyperbola. So your final equation will be x minus 1 the whole square by 25 upon 4 minus y minus 4 whole square upon 75 by 4 equal to 1. Okay, now I'm leaving it at this stage because I don't want to waste time simplifying it. My idea was to convey the concept. So how to deal with the equations when some critical information about the question is provided to you. Next concept that we are going to talk about is the concept of focal distances. Focal distance of a point from the two foci. So let's say I take a standard case of a hyperbola. So let me pick up a point. Let me pick up a point over here. So what are the distance of this point from this focus and what are the distance of this point from this focus is what I'm interested in. So let's say this is P and let's say this point is S1, this point is S2. Okay. So assuming this point to be X1 comma Y1, let us find out S1P and S2P. That's called the focal distances. These are called the focal distances. Now S1P can be found out very easily because let's say I drop a perpendicular over here and I call this as M1 and I call this as M2. S1P is E times PM1, which is going to E times X minus X1 minus A by E. That is going to be EX1 minus A. This will be E times PM2, which is going to be E times X plus A by E, which is EX1 plus A. Okay. And when you take the difference of these two, mod of S1P minus S2P, you're going to get 2A. This is a very important piece of information for us, which says that you can also define hyperbola as the locus of a point which moves in such a way that the difference of its distances from two fixed points is a constant and this constant is lesser than the distance between the two fixed points. Between the two fixed points and not 0. Is that fine? So please remember this. This definition is very important in solving questions which come related to complex numbers also sometimes. Okay. Next is the parametric equation of a hyperbola. Parametric equation of a hyperbola. X square by a square minus y square by b square equal to 1. Okay. Now normally we represent the parametric equation of a hyperbola to be x equal to a sec theta and y is equal to b tan theta, right? Where theta is a parameter which is called the eccentric angle also. Theta is called the eccentric angle. It actually behaves as a parameter. Okay. Now let me just show you what is this eccentric angle actually. So let me hide this. Okay, so as you can see on your screen over here, I have drawn for you a circle whose diameter is exactly the distance between the vertices. Okay. By the way, this circle is actually called the auxiliary circle. This circle is actually called the auxiliary circle. Right? All of you please pay attention over here in this auxiliary circle. What I'll do, I'll make an angle theta from the origin like this. So let's say this is angle theta. Okay. And from this point, I'm going to sketch a tangent. Okay. So what I did, I took an angle theta and I sketched a tangent at this point. And this tangent, I'm going to take the point of intersection over here and scale it up till it hits the hyperbola. So what I did first, I made a 90-degree tangent over here. This tangent meets the transverse axis at this point. Let me name this point. Let's say this point is the point P. From this point, I took a perpendicular up to cut the uh, hyperbola at, let's say, point Q. Then we say that the coordinates of Q will be A sec theta comma B tan theta. So this is how this angle theta is related to this point Q. Many people wrongly believe that this angle is basically the angle made from here to this point, right? And they think that this angle is theta. Please no, that angle is not theta. By mistake also, please do not take that. Is that fine, guys? Now, if I take the parametric equation of, if I ask you the parametric equation of this x minus alpha square by a square minus y square, sorry, y minus beta whole square by b square equal to 1, then what would be the parametric form? The parametric form would be x equal to alpha plus a sec theta and y will be beta plus b tan theta. So this will become the parametric form. And if you have the conjugate x square by a square minus y square by b square equal to -1, then its parametric form would be x equal to a tan theta and y equal to b sec theta. Okay. Now guys, various type of parametric forms are also possible. These are the most commonly used ones. So I'm not saying this is the only way to represent parametric equation for a hyperbola. Okay. So let us take some questions to appreciate other forms that can also be possible. For example, let's take this as a question. Prove that a by 2 t plus 1 by t comma b by 2 t minus 1 by t. This point lies on the hyperbola. And get the equation of the hyperbola as well. Get the equation of the hyperbola as well. Yeah, so here t is a parameter and you need to actually eliminate t in order to get the equation of the desired hyperbola. Correct? So first let us look into this aspect. So x is equal to a by 2 t plus 1 by t, and y is equal to b by 2 t minus 1 by t. Okay, so I can say 2x by a is t plus 1 by t, and 2y by b is t minus 1 by t. Now when you square both the sides, so you get t square plus 1 by t square plus 2. Here you get 2y by b whole square as this t square will not come. This becomes t square plus 1 by t square minus 2. Now let me call this as 1. Let me call this as 2. Let's subtract 1 minus 2. That gives you 4x square by a square minus 4y square by b square is equal to 4. Drop the factor of 4. So you get the equation to be exactly the standard case of a hyperbola. So even this could be used as a parametric form. So my point is, don't be like under the impression that it is always a sec theta comma b tan theta. Okay. Next question. If E and E dash be the eccentricities of a hyperbola and its conjugate, then prove that 1 by e square plus 1 by e dash square is equal to 1. Then prove that 1 by e square plus 1 by e dash square is equal to 1. So please type done if you're done with this. It's an easy problem. Probably you would have done this in school as well. Alright, so only Lalita could do it. Simple. So for the normal ellipse, we have e square as 1 plus b square by a square, which is actually a square plus b square by a square. And for the conjugate, this will be 1 plus a square by b square, which is actually again a square plus b square by b square. So when you reciprocate these two and add it, you get a square by a square plus b square by a square plus b square. That is clearly your a square plus b square by a square plus b square. That's going to be 1. So next concept that we are going to talk about is the concept of position of a point with respect to a hyperbola. Position of a point with respect to a hyperbola. Guys, can you see the screen? All right, so let's again make a hyperbola. Now, a point can be at three locations with respect to a hyperbola. It can be at a position A, it can be at a position B, or it could be at a position C. Okay, so let's say the point A here is the point here is x1 y1. Okay, let's say x1 y1 is the point, and I want to find out whether it's located somewhere within the arms of the hyperbola, that is at position number A, or whether it's located on the hyperbola, or whether it's located outside the arms of the hyperbola. Now guys, in case of a hyperbola, the situation is slightly different. If the point is at A, then if you substitute A in place of x and y for this hyperbola, you would realize that x1 square by a square minus y1 square by b square is actually greater than 1. Right? That is x square by a square minus y square by b square minus 1 will be positive. If it is at situation number B, then you would realize x1 square by a square minus y1 square by b square minus 1 will be equal to 0. And if it is at position number C, x square by a square minus y square by b square minus 1 would be less than 0. Okay. Again, this expression is called S. X square by a square minus y square by b square minus 1. This is called S. And when you put the point in place of x and y, this is called S1. So this is like saying S1 is greater than 0. This is like saying S1 is equal to 0, and this is like saying S1 is less than 0. Okay, so it is inside if it is greater than 0, on if it is equal to 0, and outside if it is less than 0. Okay, next is the concept of intersection of a line, intersection of the line y equal to mx plus c with the standard case of a hyperbola. Again guys, the concept is pretty much same as that we had for an ellipse. What do? We try to simultaneously solve these two. Okay, by substituting y as mx plus c in the other equation. So that gives you x square by a square minus mx plus c whole square by b square equal to 1. And if you simplify this, you are going to get a quadratic equation in x like this. Okay, and just by deciding the nature of the roots of this quadratic equation, you can actually make out whether the line is cutting, touching, or not even touching the given given hyperbola. Okay, so there can be three situations. There can be a situation where it is tangent like this. There could be a situation where it is cutting like this. And there could be a situation where it is not even cutting like this. Okay, so how do we distinguish between situation number A, B, and C? Just by looking at the discriminant of this particular quadratic equation. So I'm just going to write down the result. I don't want to waste time simplifying this. Okay. So if c square is greater than a square m square minus b square, it will be situation number A. That means it will cut the hyperbola. If c square is equal to a square m square minus b square, it will be situation number B. That means it will touch the hyperbola. And if c square is less than a square m square minus b square, it would be situation number C, that it will not touch the hyperbola. And please remember, these conditions are very much specific to this hyperbola only to be applied on the standard case. Only to be applied on this. Okay. So if your hyperbola changes, your situation will also change. Your situation will also change. Okay. Out of this, the condition number B is actually called the condition of tangency. This situation is called the condition of tangency. Right? And because of this, you can actually write the equation of a tangent, if you know the slope, as a square m square minus b square. This is called the slope form. This is called the slope form. Okay. So guys, a quick analysis about this equation. There is something very important about this equation. So when you say the slope form, which is y equal to mx plus minus under root a square m square minus b square. Please remember one thing, that you cannot draw tangents with any given slope. Your slope must be following this restriction. That means a square m square should be positive. That means a square m square should be greater than b square. That means m square should be greater than b square by a square, or m square minus b square by a square should be greater than 0, which means m minus b by a, m plus b by a should be greater than 0. That means m should either be greater than b by a, or m should be less than minus b by a. Right? In other words, let me tell you what is b by a and minus b by a slope. In fact, I'll just take you to the GeoGebra setup. Let's say I draw a slope of y is equal to b by a slope line. So y is equal to 2 by 3x, or 2x by 3. Okay. This is b by a slope, and y is equal to minus 2x by 3. Okay. So please remember, the slope of the tangent that you are going to draw should be either be greater than b by a or less than minus b by a. That means your line could have slopes of this nature. It could be like this. It could be like this. I'm just drawing the slopes. I'm not drawing the exact tangent. So basically what I'm trying to say is that this zone is the zone in which your slope should lie. If your slope happens to be lesser than that, what will happen? It will end up cutting the hyperbola. Okay. For example, let's say I take a slope like this. I can always shift this and make it a tangent like this. Are you getting this point? But if you try to take a line with a slope, this, no matter wherever you shift, no matter wherever you shift, it will end up cutting the hyperbola. Are you getting this point? So you can never get a real tangent. You can never get a real tangent if your M happens to be, let me write it, no real tangent. No real tangent. If your M happens to lie between minus B by A and B by A. So it has to be either less than minus B by A or greater than B by A to get a real tangent. To get a real tangent. And another thing which I want to tell over here is that, which many people tend to get confused, there cannot be any tangent which actually is tangent to both the arms simultaneously apart from these two asymptotes. So asymptotes are only two such tangents which are simultaneously touching both the arms. So these are like tangents to both the branches at infinity. So asymptotes can only touch both the arms simultaneously, and this point of touching is at infinity. Rest no tangent can touch both the arms simultaneously. For example, let's say I make a tangent like this. Okay. Now this tangent can never touch the other branch. If it is touching over here, it will not touch the other branch. Okay. So no tangent can touch both the arms of the hyperbola simultaneously except for the asymptotes, and for the asymptotes they touch the arms simultaneously at infinity. Is that clear, guys? So what we'll do is we'll take some quick questions and wrap up this session, because I know many of you are having exams also. So let's take this question. Show that x cos alpha plus y sin alpha equal to p touches the hyperbola x square by a square minus y square by b square equal to 1 if a square cos square alpha minus b square sin square alpha is equal to p square. Done? So Lalita is done. So very simple. Use the condition c square is equal to a square m square minus b square. So remember c over here will be p by sine alpha. Okay. A square m will be minus cos alpha by sine alpha whole square minus b square. So multiply throughout with sine square alpha. You will get a square cos square alpha minus b square sine square alpha. Okay. Hence proved. Next question. For what value of lambda does the line y equal to 2x plus lambda touches 16x square minus 9y square is 144? Please type in your response in the chat box. Four. No, that's not correct. How about Rohan? Rohan, any response? It's a similar nature question. Root 20. That's correct. Okay, let's apply this. First of all, we write it in a standard form. So 16x square by 144 minus 9y square by 144 equal to 1, which means x square by 9 minus y square by 16 is equal to 1. Okay. Now a square is 9, b square is 16. And for our case, our c is equal to lambda and m is equal to 2. Now it will be tangent only when, since this is a standard case, it will be tangent only when c square is equal to a square m square minus b square, which means lambda square is equal to a square 9, m square, which is 2 square, minus b square is minus 16. That means lambda square is equal to 36 minus 16, which is 20, which means lambda could be plus minus root 20. That means lambda could be plus minus 2 root 5. Okay. So all right, guys. So we'll call it a day now. However, we have many more concepts left to be covered in case of a hyperbola. So we'll be talking about other forms of the equation of the tangents, like the point form, parametric form, etc. Then we'll talk about the other equation of normal, again in Cartesian form and parametric form. Sorry, point form and parametric form. Again, repetitive concepts like chord of contact, pair of tangents, chord whose midpoint is given to us, concept of pole and polar, equation of the diameter, concept of conjugate diameter, concept of conormal points. So all these concepts, and apart from this, there is a very small part of a hyperbola which is called rectangular hyperbola, and asymptotes that we need to cover up. So I think the next class that we'll be having will be covering up all these concepts as quickly as possible, so that you are well prepared with your conic section part. And it's good that we are doing it towards the end, because these concepts will be fresh in your mind, because they're done normally in class 11, then people tend to forget them. Okay. So thank you so much for coming online. So over and out from Centum Academy. Thank you, and best of luck for your exams. Bye bye. Have a good night.